published around 100 peer reviewed international research papers and delivered various national and international talks on advanced nanostructured materials, their synthesis and characterization for various applications such as photocatalytic water purification, electrochemical sensors, and energy storage applications. She worked as a guest scientist in University of Duisburg, Essen, Germany, and Ural Federal University, Russia. She has various research grants, including Nano Mission, which is sponsored by DST, Early Career, sponsored by SCRB, UGC, and BRICS. We welcome you, ma'am. Please continue, ma'am.
Okay, thank you very much for such a nice introduction. And thank you, Professor Amit sir, Head Microbiology Department, and the rest of the faculties also. I'm very grateful for giving me the opportunity to present the work on this applications of scanning electron microscopy and transmission electron microscopy. Okay, so uh, so basically, this is our nano center, and its inauguration being done 5 years back. So here the logic or reason behind putting this picture as a starting one is Professor Izima. Professor Meto Izima. His slide will also come later.
Ma'am, can you
And
please make it full screen?
okay,
Yeah.
is it clear now? Yeah.
It is clear now. Yeah, it is clear.
Yes. Thank you very much.
It is clear now.
Yes. So he basically done Professor Izima done lot of work on transmission electron microscopy, specifically for the carbon nanotubes. So one of the pioneer person who is known for his work on transmission electron micrographs. So spent more than 15 to 20 years specifically working in this area only. So transmission microscopic studies of nanostructured materials, and in that specifically one-dimensional carbon nanotubes. So he basically did the inauguration of our nano center in 2016, November, 4th of November. Then we have rest of our members, project members of BRICS multilateral project, our former director also Professor Islam, my one of the PhD supervisor, Professor Shiv Prasad, presently Karnataka Higher Education Director, and most important this DST Secretary and INSA Chairman also Professor Ashutosh Sharma. So in the presence of all these uh, uh, legend people, we did the inauguration of our Nano Center. As now moving to the slides, so it's basically uh, our presentation comprises applications of scanning electron microscopy and transmission, specifically for the nanostructured materials, their types, zero-dimensional, one-dimensional. So with as we move on, we will keep on discussing about them also. Then some specific configurations, core shell, monodisperse, and their this instrumentations application in case of nanoscience and plant soil systems, in the biomedical field also, in the for the studying of antimicrobial activity also, we are going to study the role of these important instruments. So as mentioned about Somio Izima, Japanese physicist who often cited as the inventor of carbon nanotubes. He has worked to discover and elucidate the atom structure and helical structure multi-walled and single-walled carbon nanotubes using transmission electron microscope. Specifically, he has developed high-resolution transmission electron microscopy (HRTEM) in the early 1979 and laid the foundation of the current HRTEM. So in our nano center, we have high-resolution transmission electron microscope. Now, presently, this instrument has been installed at various places like AIMS also. In IIT Delhi also, we have it since 2007, latest one, HRTEM. It's in Indian IUAC, Inter-University Accelerator Center. Now recently installed in Jamia Hamdard also, where you people can easily approach within Delhi for the characterization of these instruments. Even Jawaharlal University also, National Physical Laboratory. So all these places. So benefit of being in Delhi that we have this transmission electron microscope at multiple places. Now here, this why this transmission electron microscope is so important. So basically here, I'm going to refer Feynman and nanotechnology part. Feynman lecture series is very famous and it's very much known as the father of nanotechnology. So uh, his work is there is a plenty of room at the bottom. Basically, it refers to that once you reach the nano dimensions, then there is drastic change in the properties. Say you consider bulk gold, which is yellow in color. But when you go to the nano dimensions here means 10 to the power of -9, then color of gold changes. Not only changes, say from yellow to red, or it can change from red, black, blue, green, means depending upon the size further in nano dimensions, we can change the color, which is clearly visible through naked eye also. But if we want to see what actually happened at a dimension level, at atomic level, we need these type of instruments. So in 1959, Feynman gave a lecture speculating on manipulating and building machines on the atomic or molecular scale, which is also known as nanotechnology. So here we try to correlate importance of transmission electron microscopy in nanotechnology. Means if you want to study the nanomaterials, these instruments are must. Otherwise, there is no direct proof of seeing nanoparticles. Today we can see and move individual atoms with the help of atomic force microscopes. As further, nowadays this quantum computers, quantum cryptography, quantum communication. So what is this quantum? So nanotechnology and quantum physics are also linked, or quantum technologies are also linked. So here in few following slides also, we are going to study how nanotechnology is linked with the quantum part, and then how all quantum applications to understand them also at materialistic level, means at the material manipulation or material articulation level, we need to have transmission electron microscope. So some of the instruments we have at our nano center, as mentioned, nowadays at many places also, these are the instruments at JNU also, they have their specific center, SAF, and this Delhi University also, in IIT also, we have NRF center where all these instruments which are required for the studying of materials available. So understanding this scale, so it basically say we are moving from say human scale to below atomic scale. So as the dimensions reduces to say from this -6, where we used to see the bacteria and all, and at -9 and -10 for atomic scale, where we used to talk about the nanotechnology, we specifically say this range or refers these dimensions under the study of nanoparticles. That particles of size less than 100 nanometer, we usually call them as one of the definition, but more precisely, we used to say that when the phenomena of quantum phenomena has come into the existence, then we say that actual change in the particle properties is possible. Now, understanding how these requirements have come into this, to see the particle or to address the issue, we need to have the tool of that particular range only. Like with the help of eyes, we can see up to 10 to the -2, -9. Now microbes, which are known as microscopic particles, 10 to the power of -6. Micro is 10 to the power of -6. So here we have light microscope. Then further to look below to this range of -7, -9, we need to have electron microscope. And in this further with time, From normal transmission electron microscope, we have further high resolution transmission electron microscopes, where we can actually see interplanar spacings also. This is also one of the picture to show uh, that normal photo taken with the optical microscope and then taken with the scanning electron microscope. Just few images to show that importance of these images and how the resolution improves if you use the correct tool. Means wherever we require the sword or where we used to have the use needle. It's basically like this. So nature of electrons. So basically in transmission electron microscope, our tool is electrons, because electrons wavelength is of the order of 10 to the minus 8 or minus 9. For microscopic, like normal light microscope, we use visible light, which is 400 nanometer to 700 nanometer. So we used to have the tool as per the uh, object which we want to look. So here the nature of electrons include having wavelength that are much shorter than that of the photons. So that's why in transmission electron microscope, instead of using normal light rays, we are using the electrons. And if you correlate with normal quantum part and all this, that these electrons are known for their both light particle characteristics as well as wave nature. So here we use these features also. So with the optical microscopes, resolutions are of the range of 1500 times only, and 200 nanometer resolution. Whereas with the scanning electron microscopes, we are capable of much higher resolutions. And further with high resolution transmission electron micrographs, further high resolutions are possible. As mentioned, nanoparticle size and this change. So nanoparticles, basically we have nano range, say nano rods here. One example in this image, nano rods, where we have different aspect ratios. Different aspect ratios means different length to width ratio. Here not all dimensions in the nano range, only the thickness of the rod. Maybe you compare, say you have a pen or say you have a wire whose thickness or whose width is in the nano dimension, then also one can see the effect of nanotechnology, effect of change in properties. And here which is visible is the color. You can see that as the aspect ratio changes, color changes from blue, green, and then finally to the red. This is the power of nano dimensions. And to see these nano, that how much, say 15 nanometer to 12 nanometer to 10 nanometer to 8, how these color changes, we should have the that much precise instrument also. So nanotechnology is not at all possible without the help of these instruments. Nano shells, nano cages. So these cage-like structures in nano is very famous. Later on, we will have some images also of metal organic frameworks, where basically these cage-type structures are useful for the capturing of various type of pollutants, especially these industrial pollutants like carbon dioxide. So we want to capture. So we need cage-like structures. So cage-like where all the gas to be trapped. So how much is the pore diameter, pore size? Some direct techniques are there and some indirect techniques are there. Indirect technique is BET, which is used for the determination of pore volume, pore size. And direct technique is again these instruments which directly see the morphology. Some more examples: zero-dimensional, one-dimensional nanostructures, two-dimensional, three-dimensional. So they are classified as per their dimensions in the nano range. 0D here basically refers to that all three dimensions in the nano range, -9. One dimensional, like carbon nanotubes, nanowires, composite nanowires. Now we further have these nanotubes, nanobelts, nanofibers. All these are one dimensional, but they differ. Like nanorods are solid structures. Nanobelts are also solid structures, whereas nanotubes are hollow in nature. So how we will know through this transmission electron micrograph, it is possible to know whether these are hollow structures or the solid structure. Now say both nanorods and nanobelts are solid in nature, then difference come through their cross section. That in case of nanorods, cross section is circular in shape, whereas when we have the belt shape one-dimensional nanostructures, then the cross-sectional is rectangular in shape. So through this cross-section, we further do the analysis whether this one-dimensional is nanofibers, nanowires, nanorods, nanotubes, nanobelts, like this. We have two-dimensional nanostructures, also graphene, which is Norselov, famous Nobel laureate, known for his work on graphene, and many applications nowadays with these 2D materials. And if you want to see the graphene, basically its bulk is graphite. When you further do its mechanical exfoliation or liquid phase exfoliation, we keep on reducing the size or keep on removing the layers. Once you have the thickness in the nano range, means say when you have only 4 or 5 layers, then the thickness is in nano range, then the quantum confinement effect have come into the picture. Then properties drastically changes. Again, these 3 dimensional we have mesoporous structures. So nanomaterials which have tremendous applications specifically in this photocatalytic activity because of their high surface area. For photo water splitting also, for antimicrobial activity also, for biosensors. So nanomaterials are everywhere. So wherever is the nanomaterial, we need to characterize them through these SCM and TM instruments only. Now here, one concept of quantum confinement, that nanomaterials, why they are so special? Because we have quantum effects. Quantum effects basically refers where we have change in the properties. We know that from our childhood that metals are those which are good conductors of heat and electricity. But when the same gold or same silver, which are known as the best conductors, but when they reduce to the nano dimensions, they become insulator. So electronic properties changes in the nano size. Now here in this picture, we are showing the change in the color, which is optical property. So in one image also earlier, it's being shown that color changes from red to blue, depending upon the color is basically related with the band gap. We all know that zinc oxide, all of you have mostly prepared or work on it, that it has very high band gap, 3.3 electron volt. But when same zinc oxide or same, say we prepare some quantum dots of say CDSC or graphene or boron nitride, nowadays these carbon quantum dots, with change in the size, we have the different colors. Maybe many of you have done some experiments also on CDSC quantum dot preparation, where you have seen that with the change in the surfactant concentration, when you have the capping agent concentration variation, different size quantum dots are achievable, and then they have different band gaps. Different band gaps means difference in the color, and difference in the color, difference in the size results in the different application part. So here some zero-dimensional nanostructures, specifically these mesoporous silica nanoparticles. So zero dimensional, as we mentioned, we have graphene quantum dots, carbon quantum dots, fluorines. Inorganic, we have CDSC, CDT, magnetic quantum nanoparticles, which are very much useful for this gadolinium based, for these MRI applications. People used to do with some magnet brain mapping when we have this MRI studies. Polymer also dots available nowadays. So zero-dimensional nanostructures have novel properties: optical, wavelength-dependent photoluminescence, chemical inertness, cellular permeability, and biocompatibility. That's why quantum dots have a lot of applications in range of drug delivery also is one of the important application of nanomaterials, specifically these quantum dots, bioelectronics, biosensors. Now here this, all of you may be that Nobel Prize in chemistry is given to these 3 people, specifically for their work on quantum dots. Chemist Monge, chemist Louis, physicist Alexei, both Russian physicists, So basically all three at different places working on the quantum dots from last 20 years. So Nobel Prize being given not only because they are important, specifically for the application, specifically the huge potential they have in a number of applications. So 2023 Nobel Prize in Chemistry is given to the work on quantum dots. Now, some simple definition is given. So quantum dots are ultra small with made up of 100 to 10,000 atoms with the size range of 1.5 to 10. So average distance between electron and hole is basically called the exciton Bohr radius. So when the size is less than this, then we used to have the quantum effects, and we call this particular nanoparticle as a quantum dot when size dimensions are lower than the excitonic Bohr radius. So earlier also we have discussed, so nanomaterials are known for their high surface to volume ratio and unique these physical, chemical. We have this super paramagnetic effect. We have superconductors at room temperature when particles, and then we have this when you come to this new, as all of you know that this year lot of budget has been passed for quantum technologies. So this for quantum information, maybe some of you have studied about NAND gates, NOT gates. Gates, basically all this electronics is based on silicon chips, NAND gate. But nowadays we are planning to make the same gates using quantum based materials. So about 6,000 crores of fund has been passed for the quantum technologies. And under this, quantum materials is one of the important field. Next point is this energy band gap increases. This is also one of the feature of nanomaterials, that as you change the size or decline the size, there is increase in the band gap. And band gap govern lot of properties. So again, one more image just to show that with the size, color changes, and color changes means change in the optical and electronic properties. Here one of the image of carbon quantum dots, TEM image, and high resolution SEM image to show that how it looks. So look at the scale. Scale is say this 100 nanometer, and this, if you look at the size, they are very, very small, say less than 5 or 10 nanometers only. Then through this online softwares are available where you can individually mark the its images. Software is easily available. And this maybe most of the time when you go for the purchase of TV, this quantum LED TV, QLED, Samsung new range of TVs, because these, as mentioned, these quantum dots. Now you see the advancement in the television technology. That how means now we have plasma based TV, now QLED based TV. So where we have quantum dots, such bright colors. So in previous images you have seen that these bright colors with quantum dots. So new range of TVs, there are research centers working on this QLED based televisions nowadays, Samsung new range. So quantum dot TV, quantum LED can be made to eventually replace organic LEDs. Here the point is when to use this scanning electron microscopy and when to use this transmission electron microscopy. Basically, transmission electron microscopy is used. Here we see the transmitted electrons to make the image. So sample. So since it has to transmit the sample, it has to be very, very thin. So if the sample is not thin enough, then we can't use the transmission electron microscopy for seeing the particles. Then we go for the scanning electron microscopy. Some more images, scanning electron micrographs for this carbon quantum dots at different resolutions, 300 nanometer, 100 nanometer. Then the same images with the transmission electron micrographs, 100 nanometer, and then if you look at right scale is only 2 nanometer. So why this word HR temp, where you can see within it, say within it, so interplanar spacing, say you have prepared different and say mixed two types of carbon quantum dots, CDSC and CDT, or say you have let's take the very simple example. Say in periodic table we have 100 and 105 elements, or more than 110 say. So every element is unique in terms of its number of protons in its nucleus. Similarly, all elements possess a crystal structure or some interplanar spacing where their attractive and repulsive forces balances. That is called the lattice constant. So further in this lattice constant, we say that different crystal structures you used to study. Say this zinc oxide has hexagonal structure, or sodium chloride has cubic structure. Now there are some interplanar spacings also, which is also fixed for that particular element. So how to know actual that interplanes means within the crystal you are seeing, within the crystal, within the atom you are seeing the planes. That is possible only through this HR term. So understand the power or resolution power. Say you see now use normal specs, then you see use this normal light microscope. See this transmission electron microscope. Now it's high resolution transmission electron microscope where you are seeing this interplanar spacing of 0.21 nanometers. So SAM and TAM image comparison, 300 nanometer at using SAM, 100 nanometer then TAM, and then further 2 nanometer scale. And within this 0.21 nanometer. So this spacing is marked through the image software while carrying out the uh, studies, or later on also it can be done. There are various methods available for the synthesis of carbon quantum dots. Maybe most of you have done the synthesis also. Some more images of carbon quantum. Now here the two have been combined, carbon quantum dots with silicon oxide nanocomposites, so different. And then we have this elemental mapping also. You can see that say we have these four elements within it. So we have silicon, oxygen, carbon. So it's kind of what are the elements present in this. Nowadays, these scanning electron microscopes come with the attachments also, where you can have this EDEX, energy dispersive analysis, where you can have the what are the elements present in the given material also. So that is also possible. Although there are various other techniques also for the study of elemental elements present in the given material, like we have this X-ray photoelectron spectroscopy. We have X-ray electron photoscopy, which is also known as ESCA. Uh, for the study of which is based upon the basically this as mentioned that every element is unique in terms of its number of protons in its nucleus. Now proton, now we have the shells, K shell, L shell, M shell. Now say if I take the example of sodium, so its atomic number is 11, electronic configuration is 281. So we have 2 electrons in the say K shell, then we have further 8 electrons. So these 2 electrons in the K shell is having some particular binding energy with the nucleus. Then 8 electrons have different binding energy. When we take out these electrons, they come out with the specific energy. So with this, we are able to label that from which element these electrons belong to. So one of the technique to know what are the elements present in the given sample. So here also this SAM is different from XPS is totally different, and here in this scanning electron microscopy, this is totally different. But here we have one attachment. Through this, we can do the elemental mapping, that what are the elements present in it. Here again, carbon quantum dots with mesoporous hematite. You can see different this images. No, just images are shown. Whenever nowadays you go for the scanning electron microscopy analysis, simultaneously you can see now the option of this EDS analysis is also available. Say they are costing say 600 rupees for the SAM micrographs, then 200 rupees for the coating, then again the 400 rupees for the EDS mapping. So with this you can see the elements or the total package is also available whenever you go for the characterization of these prepared samples. One more, transmission electron micrograph of carbon quantum dots, and again the high resolution image with the specified interplanar spacing of 0.32 nanometers. So earlier it's the different, now it's 0.32. So all dots look same, but with this HR10, you can actually point out whether it's carbon quantum dot or say this, or if you have say done silicon based or say CDSC based, interplanar spacing helps in doing it. And here further, right side image, you can see further carbon quantum dot in this MH composite. So with this HR10, we are able to segregate both the parts also. So with enough of this carbon quantum dot and this MIL, basically this metal organic based uh, structures which are specifically used for their photocatalytic activity. So graphene PBS based structures. So here again we have FESM and TEM images to show that uniform distribution also. Graphene sheets basically say, as we say, it's the flakes. So we have to do some cross sectional or to know the width, whether we call it as graphene 2D structures. So a lot of images shown on quantum dots. So when you prepare the quantum dots of different sizes, they will show the different colors also. So maybe all of you have seen this 2023 Nobel Prize video also, where they have these type of images to show the significance of nano dimensions. So applications, light emitting diodes, photoconductors, photodetectors, catalysis, QLED as mentioned, TB, photovoltaics, biomedicine and environment. Environment is basically photocatalytic activation, where we used to do the degradation of various organic pollutants using carbon quantum dots. Further bioimaging, clinical applications, drug delivery, biosensing, all this using carbon quantum dots. So in this carbon quantum dot specifically for this fluorescence means byproduct, and then used for this cell imaging and bioimaging experiments for cytotoxicity, antioxidant activity, and overall performance. Again, the use of carbon quantum dots in these areas. So some quantum dots prepared in our lab also in similar way, and their size is around 6 nanometers. So FESM and this HR10 images of carbon quantum dots. Moving further, so graphene-based quantum dots, now one application of this that difference in the size, and then basically we have different photocurrents also with the change in the size. Now comes here one more point. Here we have this comparison with the atomic force micrographs also. This atomic force micrograph also is one of the way to see the morphology of the particles. So here this first image here is the 3D view of the core shell PBO nanoparticles, and the same image is taken using transmission electron micrograph. So this is our own paper in 2007, where we have HR10 installed in IIT Delhi. So this of my work is published in Journal of Nanoscience and Nanotechnology at that time. So it's a three-dimensional view, and you can see that how uniformly size these particles are. Core shell is named because PB is core, and it's surrounded by the shell of PBO. So oxide layer is present around it. And further with this AFM image, we are able to know that how much is the shell thickness and how much is the interface area, interface region, and then what is the size of the core. Now, core shell nanomaterials are also very much popular because of their tremendous advantages. Now, to determine the core shell thickness, and we have done line cross section also. I'll show you. So this is the normal. We have done the sputtering. Sputtering is basically the removing the top layer. So how it is done? So basically, the experiment we performed is like in IIT Delhi and National Physical Laboratory. In National Physical Laboratory, we have X-ray photoelectron spectroscopy (XPS), and in IIT Delhi, we have atomic force microscopy. So what we used to do, we placed over this PBO portion nanostructure under this X-ray instrument, XPS instrument, and sputter it. We sputter it means we remove the top layer. Say we remove the top layer, basically we are removing the oxide part. Say we remove the oxide part, then the core part will start. Imagine it like the egg. Egg, say your yolk is your core, and then your protein part is your shell. So we want to see, you will keep on slicing. So same slicing we have done in XPS. Then say we have done the 5 nanometer slicing. Then we take it out from the National Physical Laboratory in the morning. I carried out the experiment when I was means as a PhD student only. Then used to take it to the IIT Delhi. There I used to perform the AFM, and in 2007 only. So it's basically the first image is 5 nanometers. If you look, it's the you can see the line scan. So once then again after carrying out the AFM, we will take out the sample from the AFM. Then again come back to the National Physical Laboratory. Again do the sputtering. Then it's a 15 nanometers now sputtered, say 15 nanometer slice from the top. Then again we'll take it back to the IIT, and then again do the line scan and see the image also. So this process is done, and then finally we are able to get the core shell nanostructures. This is one of the direct way to seeing and then slicing it out. Maybe in later references, this paper will come where you can refer it also. There are many other ways also to determine the core shell nanostructures, means through directly XPS also, where we say it's say when lead is bonded with the oxygen, then it's in the state of Pb+2, and when it is in the core, it is Pb0 state. So Pb+2 electrons, +2 state and Pb0 state. So basically, their core levels have difference in the binding energy. So basically, from XPS, from these core levels, we know that whether the signal is coming from the shell or the signal is coming from the core. So this is also one of the indirect way to find out the thickness of core shell nanostructures. And here, the method right now is mentioned is direct slicing, and then seeing the actual image through atomic force microscopy. We have correlated with the results with the XPS system also. Yes, it's here. So this XPS depth file of say first region, second region, third region, this Pb+2 signal is falling because Pb+2 is only in the shell. If you keep on removing the outer part, keep on slicing, finally this +2 signal decline, and Pb0 signal, which is the core signal, will keep on emerging. So you see Pb+ signal is keep on declining, and Pb0 signal is keep on rising. And Pb+2 signal if declines, it means oxygen signal also declines, because Pb is +2 means lead oxide. So you see this oxide core level is also following the Pb+2, just mimic the Pb+2. So this whole graph is plotted not by just 2, 5. Basically the core levels are taken, and then from 2 minute, 5 minute, 10 minute, this 8 minute, 12 minute, all these samples have been spotted. Actually, this is not the one-day experiment. This is more than 1 month or 2 months experiment, because XPS is performed under vacuum conditions. And when you sputter, basically you destroy the vacuum. Again, the system will achieve the vacuum. And vacuum is not here the rough vacuum. Say in air present is 1 atmosphere. When you go through the mountains, pressure reduces. But in most of the instruments, like in this transmission electron microscope, this X-ray, XPS, X-ray photoelectron spectroscope, you have the ultra high vacuum, means 10 to the power of -8, -9. Till 10 to the power -3, we used to say that it's a rough vacuum, which is achievable within 1 hour or half an hour. But to achieve -6 or -9 vacuum, you need the process of minimum 4 to 6 hours. And again, once this vacuum has achieved, you will take the take the spectra of lead core level. Then again, after taking the spectra, you again slice it. And then again, slice it means again you have destroyed the vacuum. So to take the again the spectra, you have to again create the vacuum. So this process will keep on for 2 months minimum. And then in between, I want to take out my samples also. So earlier in AFM image, it's being shown that we have the image at 5 and 15 I'm showing, and even in between also. This is 30 nanometer. So 30 and then this 5 and 15 also. Basically, we have the particles in the first, second, and third region. These first, second, and third region in this D basically corresponds to this place. First, second, third. First is basically when you are seeing this PBO, lead oxide only. Second, when you are seeing the interface, basically some part is sputtered. When you see this third part is basically the core level. When you see the basically egg yolk part, and in this line scan is also there, this 30 nanometer first region, you see this line scan, it's smooth hemispherical one. When you spotted it, basically you have basically punctured it. In between you can see this hump. Again, once this hump is balanced, because remove it, this third region is basically when the core region is visible. So how this XPS and AFM and then finally transmission results are correlated. So this paper, maybe right now, maybe you have grasped only, maybe say not 100%. I'm not able to convey it in, but later on with the paper you can see it further also. One more, yes, good part here is which I want to correlate. Um, Metals again, good conductors. When we said good conductors means they are one is this high conductivity. But in terms of electronic states, we used to say that they have a density of states near the Fermi level. But how to know this density of states near the Fermi level? Which technique will help us? In this XPS, we have the provision of finding density of states near the Fermi level. Say, in the start of the presentation, I mentioned that gold, silver, best conductors, copper, best conductors. But same in the nanoform become insulator. Okay, size reduced, but how I know that it has become the insulator? I need to find out the density of states, or there are some indirect methods. Maybe you have done some Hall experiment to find out the conductivity. But this is density of states near the Fermi level. This is say here. Now I'm correlating with this PB core and PBO shell. Lead core is good conductor, so it has density of states near the Fermi level. Lead oxide is insulator, so no density of states near the Fermi level. So here, if you look at this Fermi energy graph, at zero level, there is no density of states, no hump, no peak. But as you move on, there is some density of states here near the Fermi level. At 15 minutes, what we have? At 15 minutes, basically we have removed the shell and we are left with the core part. Core part is lead, and lead means good conductor. Good conductor means density of states near the Fermi level. So how it is evident? It is evident through this valence band studies using X-ray photoelectron spectroscopy. This is how the experiment has been performed in taking all the techniques, because most of the techniques support each other also. X-ray, XRD support TAM SAT patterns, and finally, we need to correlate the results with the application also, and all techniques, morphological, structural, and this electronic are mostly in good agreement. Okay, one more, this monodispersed nanoparticles. Say nanoparticles, as mentioned, if it is 8 nanometer, 10 nanometer, 12 nanometer, 14, all have different properties. So first is, if you want to claim anything with the nanomaterials, they have to be monodispersed. Otherwise, your claims are of irrelevant. So here, again, one more paper, 2009. we reported this monodispersed palladium nanoparticles, says 15 nanometer, 20 nanometer, 25 nanometer. So benefit of being in Delhi or being in IIT Delhi that we have this instrument installed at that time, where we can actually prepare the samples and install it. However, the samples I prepared in Germany at that time, but later on the same monodispersed preparation technique is we have in IIT Delhi too. Uh, Gas phase synthesis, we have later on images also. So here these nanomaterials are prepared. Nanoparticles, monodisperse, all are of uniform size, very clearly evident. And then further high resolution image is done. So 0.242 nanometer. So nowadays is 2008 or 9 paper, which I am presenting, and presented to 2023. So imagine these instruments are now available at so many places in Delhi, although at that time only in IIT Delhi or ISC Bangalore or GNCSR in Bangalore. Uh, so maybe most of you who are working on these nanomaterials are characterizing it also. Further, this thickness of this cross section. So we have done specific this cross-sectional study. So we have determined the thickness also. It comes out to be around 60 nanometers. Okay, moving further. So this is the instrument gas phase synthesis, which is used for the synthesis of these nanomaterials, monodispersed nanomaterials, not like hydrothermal or this. Preparing 15, 20, 25 exact using this image. Prepared using gas phase. Principle is basically that the size and charge part. I'm not going into the detail of the instrument part now. Uh, Monodispersity. With this transmission electron micrograph, while doing the analysis, as I mentioned, there's software, images software also, and one is more Gatten software. It's very heavy software, but nowadays computers are also very good and CPUs are also very good. So through this Gatten software, you can actually scale your each particle. Once you scale each particle, note down the number of particles, then see that their standard deviation. It's important. So 15, 20, 25, this histogram analysis or statistical analysis have been done, and it's find out to be within plus minus 0.05% only. So here you see this standard deviation sigma g 1.05, 1.06, 1.08. So whenever this sigma is in close to this one, we should convey or as mathematical it's that it's a monodispersed particle. Okay, so now here we have scanning tunneling instrument. Scanning tunneling is again Nobel Prize achieved by these two people, Binning and Heinrich or IBM Zurich. Again, this quantum revolution which is going on. Now, again, the thing is that probably these industries, Google, IBM, maybe you know that in IBM Chennai, IBM Park in this IIT Madras Chennai, we have. So they have this quantum computer also. And this probably what I want to say is that since companies have IBM and Google have so much of funding, probably again this IBM and Google probably will win the race as compared to the academic institutes in doing this quantum revolution, because they are already in the process of making these quantum computers. So again in 1981, IBM Zurich, basically they are working there and prepared or basically invented scanning tunneling microscope. This instrument again, like SEM, TM, used to see the morphology of the particles tunneling. But here the phenomena is different, or the principle on which it works is totally different. Nobel Prize, 81 they invented, and after 5 years, Nobel Prize in Physics. So basically, this instrumentation part mostly linked with the physics part. Synthesis of nanomaterials, there are many chemical-based methods people use, or some physical methods also. And biological, we have actual real applications, especially in this drug delivery, bioimaging, and now in case of nanoparticle plant interaction also. So as I mentioned, the concept is totally different. Just a very small, within 1 minute, I will try to explain the concept. As per normal normal phenomena or whatever we observe around us, Newton's law, which we have studied in our ninth class, are sufficient to explain each and everything which is happening around us. Like you used to say that when a moving bus stops, suddenly we fall forward, or when bus starts, we fall backward, not in the reverse direction. Or when you say get out of the moving bus, you have to run, otherwise you will fall down. So basically, what I want to convey is that to explain these normal real life phenomena, which whatever we are observing around us, macroscopic objects like collision or accidents, Newton's laws are sufficient. So here, Newton's laws means classical physics. But when we go to the nanoparticles, these Newton's laws are not valid. Otherwise, for all daily life things, our Newton's law, which we have studied in our ninth class, 10th class, they are totally enough to explain each and every phenomena. But to study these nanomaterials, we need to have the concept of quantum. Now here, as per the classical mechanics, look at this hill. Now particle is here. Say if this person is on the left side of the hill and it want to go to the right side. Simple point is that you have to have this much energy, then only you can cross the barrier. As per the classical mechanics, you have to have this much energy. But quantum mechanics say it's fine, even if you don't have the energy, still you can cross the barrier, which is not possible through classical mechanics. But quantum mechanics explains it, and this instrument also based upon the quantum tunneling part. That no need to cross the barrier, just tunnel the barrier. So tunnel the barrier, then the same principle being used by this Binning and Rorer to invent this or uh, is scanning tunneling microscope instrument. So if you want to go further details, you can have its principle also. But this is simple that even the energy is less, it is possible to cross the barrier. Okay, so here again, as mentioned, this again instrument is very good. So this again instrument we have in ID Delhi at that time. So 250 nanometer palladium, this image. This is taken using scanning tunneling micrographs. And these are basically, say, a simple thing is say you have some particles, you heat it. If you heat it, or say when you deposit the material, your substrate is at high temperature, then the tendency is that particles merge. If they merge, then the size increases. So look at the left side image and the right side image. Left side image is that nanoparticles deposited at a normal, say, room temperature only. But here, the samples is prepared when the substrate is already at the temperature 250. So once they reach the substrate, they have a high temperature. High temperature means temperature and energy are linked. So they have the kinetic energy. Kinetic energy is basically energy due to the motion. So particles move and merge. Merge means size increases. So, okay, this is the theory we used to give. But this theory, we have the direct evidence through the micrographs. Sample deposited at normal temperature and then the sample deposited at 250 degrees Celsius of substrate temperature. Look at the difference in the size, and this difference and the quality of the image. Uh, the instrument is scanning tunneling micrograph based on the total different principle, and quality is, I think, superb. How these now further, again, since my part is further application part also, synthesis and application, why I'm making different particles, different size. So here just basically we prepared thin films and nanoparticles and use it for the hydrogen sensing applications. So hydrogen. So basically all of you heard about this hydrogen based hydrogen as a fuel. Hydrogen is a future fuel. But problem with the hydrogen is why we are not using in the cars. Say nowadays era has totally changed. You have a from you yourself have witnessed this quantum LED based TV. Now you are witnessing this transition from petrol diesel cars to CNG based cars. Now you are traveling in the EV based cars, right? Electrical vehicles, basically where you have batteries or supercapacitors. Now, same era, basically hydrogen-based vehicles are also there. Now, hydrogen as a fuel, problem is that hydrogen is highly explosive in nature. 4% of hydrogen air mixture causes explosion. So we need to handle it very safety. And whenever we want to talk about any new technology, safety comes first. So in our PhD, in my own PhD, I worked on basically hydrogen sensors, how to detect it. Now, let's say in normal household, also you have these cylinders for as cooking gas. They also leak. Then you smell it, and then accordingly action used to take place. But here, hydrogen being the atomic number one is the lightest gas. Lightest means highest dispersive in nature. Highest dispersive means before, even in the normal gas, you familiar with that. We used to add this ethyl mercaptan. Who smell used to smell it. You people smell it and then action used to take place. But we can't add ethyl mercaptan or any other smelling thing because hydrogen lightest before that agent comes, hydrogen disperse all over the place. Once it dispersed and this 4% of hydrogen air mixture, so big boom. So not possible. So basically this palladium being synthesized, why particular element to be synthesized, palladium has the natural affinity for the hydrogen. So earlier image I have shown you, these are of the palladium, which is one of the very expensive material also after platinum. But when we have the nanomaterials based, then we are using the very less quantity also. And in nanomaterial based we have different phenomena also which is used for the sensing. And the phenomena which works here is significantly sensitive as compared to the bulk based. That's why we have palladium based nanoparticles for hydrogen sensing applications. So here we used to sense it. Then we have published some papers also. And presently one US patent is there which referred over this work for in their patent part, which is basically hydrogen based cars is provided with the hydrogen sensors to detect the leakage, and the patent is referring this work. So this is a good achievement in itself, that our concept of this nanoparticle based palladium sensor is accepted. Moving further, this further one more part, nanoparticle and thin film. It's not the only difference in the color electronic. Basically, if you want to use this, say our nose is say, and now we try to make electronic nose. We have the sensors for the gases. We have the humidity sensor. On the traffic, this traffic police used to do this alcohol sensing. Those who have drink and drive avoid it. So sensing is an important part. So basically, your sensor is interacting with that particular gas, but to how to maximize that interaction. For maximizing the interaction, basically there are also again good theories that your this orbitals match should be there, that whatever be the gas, their orbital and your sensing orbital material should be in good overlap, in good electronic compatibility. So to know this good electronic compatibility or to enhance its electronic compatibility, nanomaterials are there. So here in this palladium nanomaterials, we have this orbital shift. So hydrogen is fixed at 1s, which is 5 electron volt below the Fermi level. So by making the nanometers, we are shifting it from 2.3 to 2.9. So if my maxima shift from 2.3 to 2.9, it means that electronic compatibility is also there. That chemisoption or physioption phenomena which are taking place during gas or material adsorption or adsorbate, they will be significantly improved. So we have formed the nanoparticles, confirmed it through the scanning tunneling micrographs. Then further through XPS, we are seeing it that the shift in the Fermi level and further enhancement in the sensing properties, we are confirming directly in application. This is how the whole picture comes. Okay, again one more image of say nanostructures. 0D already discussed quantum dots, one-dimensional discuss nanorods, nanotubes, nanoflakes, nanofibers, nanobelts, so many confinement, carbon nanotubes. There are different synthesis waves also. You people are familiar with. Now, while taking the image, now these colored images also you used to see in the papers. So whenever you take the image, just request the operator that now I'm now bored with this black and white. When TVs are colored, why my images are black and white? So take these colored images also. It's available in the software option. Make them blue, green, red. Why only have all the fashion in your fabrics only? Okay, have your paper also color one. Okay, so here again, this work we recently published, well, not recently, 2017, where we have prepared zinc oxide nanorods of different aspect ratio. The process is very simple, and this work we have in collaboration carried out with the Amity Institute of Microbial Technology, where presently I am presenting this lecture at there. So, yes, work is very much published, and say one of the most downloaded paper also in 2015 and 17, these two works, and more than 600 to one paper in this 650 citations, and then one in 120 or 130 citations of this. We have collaboration with AIMT, and this zinc oxide nanorods, different aspect ratio, SEM and TEM micrographs. And so once we have different aspect ratios, different surface area. So different surface area through BET, we have done the analysis. Difference in the band gap, that is through UV visible absorption spectroscopy, we have done it. And then difference in the application, difference in the photocatalytic efficiency also. So some micrographs showing, then further we have doped it with the copper also. Then efficiency has increased tremendously. It's used for the environmental remediation also. So here we are seeing the difference. Like environmental remediation, basically textile dyes, which are mainly responsible for the 50% water pollution is because of the textile industry. Because of the fabrics you are wearing, you want uh, passionate, basically, how to say this? Uh, Detoxify my fashion. It's same like this. So colors has to be environment friendly also. So these dyes are used which are not at all environment friendly. So we need nanomaterials which can degrade this. So here these prepared zinc oxide are used for the degradation of these textile based pollutants. Again, I say I want to do this sustainable development goal. I am targeting this clean water for all, goal number 6. So when I want to clean the water, I not only say I have taken some river sample, not only want to degrade these organic pollutants, I want to focus on these E. coli, S. aureus, these gram-positive, gram-negative bacteria, because every year millions of people, more than 20 to 30 lakhs people, kids used to die because of these waterborne diseases, diarrhea, and these E. coli, S. aureus are mainly responsible. If you look at these images, this first image is E. coli intact. This image we have taken this uh, in our paper only. And then when we interacted with the zinc oxide based materials and copper based materials, you can see cell lysis. Whole cytoplasmic content has come out. So dead mass. So these same micrographs are also helpful. Sample preparation specifically done for these materials, these conditions. And antimicrobial activity or cytoplasmic killing part is done. Uh, Very good image. This work is published in Journal of Nanoparticle Research by us in 2017. I think these holes are visible that since nanoparticles, nanorods, nanoneedles, these are very sharp. Sharp means they are able to penetrate the cell membrane. Once cell membrane is penetrated, whole cytoplasmic content will come out. The process is cell lysis and cell death. So E. coli, all that. So here the point is, water is purified not only in terms of dyes, but also in terms of these microbes. Now again, one image of the ZNO with the paper I'm talking about, more than 650 citations, where ZNO prepared with AMT students and published. Mechanism and all part are also mentioned. Then we have done this and our work with this frontiers in microbial technology, where we have done the interaction with the fungal P. indica. Very good, and it's work published in nanopartic this Nanoscience and Plant Soil Interaction. This is one book by Springer written with her and with many more chapters contributed by AMIT faculty members also, where this interaction Pindica with ZNO and done. And we have seen that how nanoparticles are helpful in increasing the root length, shoot length, and overall seed germination part also. So one more image, EDEX spectra also, as mentioned, that we can do the elemental analysis since we have added ZNO. So Z and this zinc peak is also visible. along with the others like carbon, phosphorus, sodium. Here also these are one of some of the characteristic morphologies which are possible through this FESEM. Okay, so this is okay SEM image of our nanocenter. So some principle also there. SEM uses electron beam as mentioned that for light microscope we use light. For this SEM and TEM we are basically our tools are electrons which are used to see the image or the sample. Electrons emitted from the filament, then this beam is focused and this collected from the sample to get the information of the specimen. Now, sample preparation is specifically for the biological samples. So we have mentioned this how to carry out the process, coating the sample and all this. So this various references are available for the preparation of samples also. Working principle is there, electron beam and all this, how this same instrument works. Uh, okay, so here the important part is we have this backscattered electrons. Say it's the interaction of electrons with the sample. We have backscattered electrons, we have secondary electrons, we have X-rays. So we collect all these, which all come out. We use X-rays in X-rays. We use this backscattered electrons to get the information about the composition. Secondary electrons are used for the sample morphology. So in next slide, we have this role of each of them and we collect each of them. We have different detectors, one for detecting secondary electrons, other for backscattered, then for the X-rays. Then we have, that's why it is for this elemental analysis. Then we have backscattered and then secondary for the morphology also. So all type of electrons come and different detectors are now attached with the scanning electron microscope instrument. Okay, now let's do it. It's transmission electron micrograph. Here the point is that in transmission electron, the sample has to be thin enough. Then only we can utilize it. Otherwise, it will be difficult. So we used to have our samples on the carbon grids when we want to do the analysis. So time is about to be, yes, 11. So working principle. Now here's the comparison between the SAM and TEM. TEM is expensive. Say more than 2 crores more expensive than the SAM. It's like this. So if it's just 2 CR SAM, FESAM, then TEM is around 4 to 6 CR. For samples, this is but resolution and if you want to see the high resolution transmission electron micrographs, this is mandatory. Then we have this sample has to be very thin. Then only TM can be carried out. Otherwise, we have to go for the FESAM. Some microbial images, pathogens. In plants also nowadays for various applications, we use this carbon-based, aluminum, metal-based, nickel oxide, ZNO to increase the productivity, to increase the leaf surface area. And so basically you want to do the interaction of nanoparticles with the plants. So nanoparticles means you have to do the characterization. Characterization means only through the transmission electron micrograph or scanning electron micrograph. So 20 nanometer copper nanoparticle. How? Through this only. So further, I think uh, I don't know want to close it since we are running short of time also. Say these 2D nanostructures, we have MOS2 with their interlayer spacing of 0.68, but say we have added something to make it 0.75. Now this interplanar spacing has a increased. Again, what I have done, I have again carried out, this is recently published paper by me in 2020 19 or 20 only with more than 120 citations. So here again, this increase in the interlayer spacing we have confirmed through high resolution transmission electron micrograph. So D spacing from the side patterns correspond to this. Okay, so in this transmission, we have the selected area electron diffraction also. So here we again have the planes like 001, 020, HKL planes, similar planes that you people used to get it with the X-ray diffraction. So here this attachment used to come with the temp selected area electron diffraction. So basically this is more linked with the reciprocal lattice part. So here we see the rings and then measure it interplanar spacing also. Again, this 2D and 1D combinations also. We used to prepare now 2D nanostructures, 2D, 1D nanostructures. Now carbon quantum dots decorated on 2D, 1D structures. So all these structures nowadays, uh, if you see in these papers, uh, is lot of work is done on this area. So here we prepared this MOS2 and WS2. This MOS2 sheets, now WS2 nanorods, uh, graphitic carbon nitride, polyaniline nanofibers, one-dimensional. Again, this same repetition just to see that everywhere you will find applications of these instruments. Again, these planes 100, 110. So not go for simple TAM. Request them for the selected area electron diffraction pattern also. Have the pattern of these rings, then try to correlate with the XRD part also. Or comment on this that whether your material is polycrystalline, single crystal, or amorphous in nature. This is also possible by carrying out this SAD patterns, SAED. So some more details about this also. This basically refers to SAD pattern represents secondary diffraction. It is obtained in the reverse space of lattice planes. It is used to find out the despacing of crystal planes and all this. Brighter the spot, more crystalline the sample. Amorphous materials diffuse rings because of node. So here basically we have D from this SAD patterns and then D from the XRD. This D not from SAD, from SAD pattern, and then we try to correlate with the XRD also. So how I mentioned that basically most of the techniques also in good agreement with each other also. So XRD data supports SAD pattern data, AFM data supports XPS data, scanning tunneling microscope supports application part like this. Look, these rings refers to particular planes. So probably if go through the SAT pattern studies also, one of the attachment with the transmission electron microscope. Okay, again multiple cubes, rods, cross-linked rods, microspheres. So all beautiful morphologies nowadays available. Now there's polyhedrons or bismuth vanadate. You see this type of polyhedrons also. Again, one experiment is done with this E. coli and S. aureus using bismuth vanadate. Again, the cell lysis and cell death, antimicrobial activity studies, and images are taken with this. Now, this is ZNSE, three-dimensional, probably flower-like or spheres, and then they are combined with this 2D and 3D part. Now, I want to conclude. So nanomaterials have tremendous applications, 2D biomedicine, chemical sensors, heterogeneous catalysts, gas storage, photoconductivity. Different materials are there, metal organic frameworks are there. So basically metal organic frameworks, cage-like structures, very good polyhedrons, leaf-like structures, they are there. Here we have prepared, recently we have reported this year publication only, where we have used these materials for the sensing of heavy metals. So we have 2D material and then this 67, which is metal organic framework. Now, same material can exist in 1D, 0D, and 3D forms also. Like we have MOSC2 prepared in our laboratory with broom-shaped nanomaterial. Broom-shaped. Again, we have sheets also, nano urchins also. Just vary the parameters during the synthesis. You can have 2D nano sheets of WS2, then one-dimensional nanorods of WS2. So these are some of the references, the one we have presented here right now. some of our work where we have now. I want to do the acknowledgement, specifically this uh, AIMD, for giving me the opportunity to present the work, and I'm thankful. Then funding, funding agencies, Global Challenge Research Fund is being given to us specifically for carrying out the research which is of global importance, like this environmental remediation or clean water for all. It's of global importance. These are global issues because these are affecting not the present generation but the future coming generation, threat to the future generations also. Nano mission projects also, and BRICS multilateral project, then UGC startup grant which is given to us for so finally quote, there's plenty of room at the bottom, by Richard Feynman, father of nanotechnology, and thankful to inventors of transmission electron microscope and scanning tunneling microscopes, because without this, nanotechnology was not at all possible. So thank you very much. With this, I conclude my presentation. Thank you for patience, and I hope I
Thank
have
you.
added something to the knowledge. Thank you.
Thank you, ma'am. Thank you very much for your enlightening presentation. I'll just ask audience if they have one or two questions, they can come and ask. Yeah, please come. Hmm? Yeah, yeah. Ma'am, just a minute. They're asking the questions.
Okay, sir.
Hello.
Hello.
Hello, ma'am. Good afternoon.
Good afternoon.
Ma'am, thank you. Thank you very much for this session.
Thank you.
Ma'am, I want to ask, like, as you said, we are using the nano materials for agriculture use, right? For seed priming, for the growth of the plants. So, what about the toxicity on that material,
Mhm.
ma'am, like seed and the growth of the
Yeah,
plant,
yeah.
or what we are consuming because from that plant only?
Yes, yes. You are totally right. That we have to take care of the toxicity part also. Here, the point is we have some toxicity test also, and here is mentioned like in this paper, Frontiers in Microbial Technology, where we have used zinc oxide nanomaterials because zinc is one of the micronutrient to the plants. So here basically the toxicity level basically it's basically changes with the change in the confinement or diameter. Say rods with the diameter less than 50 nanometer are toxic, but above it is compatible. Biocompatibility is there. So whenever we want to use this for the plant part, we check the toxicity part, and for the zinc oxide case, now it's well mentioned in the literature also. Go for the sizes where the dimensions are above it, not below it. Then it is not. Then toxicity is not of concern. Okay. So here also in nanomaterials we take care this part in advance. We used to take nanomaterials which are biocompatible and toxicity is already checked in advance.
Hello, ma'am.
All right.
Yes, ma'am. Ma'am,
Thank you.
ma'am, recently there is a question on nano urea also, ma'am, that IFCO nano urea. It's not that much useful for the application part of the rice production and all. Because
Mm-hmm.
like farmers are used to get the more production because of the urea only, urea fertilizer, not because
Mm-hmm.
of the IFCO urea. Because in PU, the research conducted on the rice. So they got the result like IFCO nano urea is not, or nano urea is not that much good result as compared to the nano urea. So, ma'am, I want to ask, I want your comment on it.
Yes, yes. All right, maybe this is possible that it's not helpful in increasing the productivity. But sometimes our concern is not only increasing the productivity, but we are also uh, pay attention to the rest of the parameters like their resistance to the environmental conditions or pH or the soil salinity and all this. Sometimes these things are used just to uh, increase plants' resistance to these problems. So maybe sometimes we have to sacrifice the productivity at these parameters, or maybe if they are claiming that or nano urea is used for with the intention of increasing the productivity, I think some prior experiments already done in the laboratory, then only it has to be uh, move to the crop production. First, lab scale experiments are done. Like we in AMD, we have this lab scale. First, we used to see any difference in the root germination or root or shoot. Then only once we are through at the lab level, then only it's recommended for the commercial level. But if at commercial level something has come out which is not as because promises are made only on the basis of the lab research or on the basis of the research publication, that's why it's being commercialized. Maybe some loophole is there or some or maybe some this productivity parameters compromise at the cost of resistance to the environmental restrictions or barriers.
Ma'am, there is
Okay,
decrease in protein also because of that, ma'am.
there is a
Decrease
decrease in
decrease in protein level also, ma'am, in rice.
decrease in protein level
So,
also.
so there is, we are compromising for the quality of the content, the rice
Yes,
also.
no, it's good because research is like this. We see the results, then we again reframe the experiment. And sometimes it's also important that how much concentration is being put and whether I'm assuming as such that the ideal case means as such there is no mistake from the farmers, there is no mistake say from the lab people also. But still the results as you are mentioning is there. So we have to do the troubleshooting at the level. Say if we are something is being suggested and like this nano urea and it has to play the role of increasing the protein level or increasing the productivity. If it's not doing that, then we have to look back. Okay, look back at the lab results or look back how the farmers are doing the execution or the dosage that has been suggested, is it done it in the right manner. Okay, so just we have do the reanalysis only in these cases. If protein content is reduced, then definitely then there's no need to go for the nano urea. But maybe if they have mentioned something now, the plants are able to survive under this extreme environmental condition, then maybe it's still useful to us.
Thank you, ma'am. Thank you very much.
All right.
Yes, yes, ma'am.
Any more questions? Thank you, ma'am, so much for your presentation. You were really enlightened. Please give a round of applause for ma'am. Thank you, ma'am.
Thank you very much for all of you.
Thank you, ma'am. So we close and I will be in touch and will.
Thank you.
Thank you, ma'am. Thank you.
Okay, shall I leave now?
Yes, ma'am. You can leave, ma'am. Thank you. Thank you so
Thank
much.
you.
You all can proceed for tea, high tea. Thank you.